Security control testing exists to answer a deceptively simple question. Do the safeguards we rely on actually exist and work as intended? Policies, architectures, and tool deployments all imply protection, but testing is what converts those assumptions into evidence. Without testing, controls become statements of belief rather than verified mechanisms. Control testing also serves two audiences at once, supporting operational confidence for defenders and assurance for leadership, auditors, and regulators. The challenge is choosing the right testing approach for the control and the risk, because no single method captures every failure mode or provides complete assurance on its own. Before we continue, a quick note. This audio course is a companion to the CISSP books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series.
Manual testing relies on human judgment through observation, interviews, walkthroughs, and targeted checks of specific control instances. An assessor may review how a process is performed, watch an administrator execute a task, or trace a transaction through a workflow to confirm controls are applied correctly. Interviews help reveal how controls are understood and used in practice, which often differs from how they are documented. Walkthroughs connect policy to implementation by following a real example end-to-end. Manual testing is especially valuable for controls that involve human decision-making, approvals, or exception handling. These aspects are difficult to validate through tools alone because they depend on intent, context, and behavior. Automated testing uses scripts, tools, and continuous checks to evaluate controls at scale and with consistency. Automation excels at verifying configurations, checking system states, and detecting deviations across large environments. For example, automated tests can confirm whether encryption is enabled, whether logging is active, or whether a configuration matches a defined baseline. Automation reduces reliance on individual judgment and minimizes variation between tests, which improves repeatability. It also enables more frequent testing, turning point-in-time assurance into ongoing validation. The strength of automation is not depth of understanding, but breadth and consistency across many systems. Manual methods capture nuance where automation cannot reliably interpret intent or context. A tool may report that an approval field exists in a workflow, but a human reviewer can determine whether approvals are meaningful or merely perfunctory. Manual testing can uncover informal workarounds, shared credentials, or undocumented processes that automated checks would never see. It also allows assessors to ask follow-up questions when something looks unusual, adapting the test in real time. This adaptability is critical when controls depend on human judgment rather than binary technical states. Manual testing therefore provides insight into how controls actually operate in practice, not just how they are configured. Automation, on the other hand, improves consistency, coverage, and repeatability in ways that manual testing cannot match. A script will check the same condition the same way every time, eliminating variability introduced by different testers. Automation can also cover far more instances, such as every server, every account, or every network device, rather than a small sample. This breadth is especially important in dynamic environments, where configuration drift occurs frequently. Automated testing also supports continuous assurance models, where controls are validated regularly rather than annually. Used correctly, automation turns control testing from an episodic activity into a sustained capability. Control design testing focuses on whether the control concept itself fits the risk it is meant to address. This type of testing asks whether the control, as designed, would be capable of preventing, detecting, or correcting the threat in question. For example, a control may exist, but it may be misaligned with the threat model, leaving significant gaps. Design testing is often manual because it requires understanding intent, assumptions, and risk scenarios. It is less about whether the control runs and more about whether it makes sense. Poorly designed controls can operate perfectly and still fail to reduce risk.
Operating effectiveness testing evaluates whether the control actually runs reliably over time and produces the expected outcome.
This testing examines whether the control is consistently applied, whether failures are detected, and whether corrective actions occur as intended. Automation is particularly strong here because it can verify repeated execution and detect lapses that occur outside scheduled reviews. Manual testing can also assess operating effectiveness by reviewing logs, tickets, or historical records to confirm the control functioned as expected.
Both approaches are useful, but automation scales better for ongoing effectiveness. Operating effectiveness answers the question of whether the control works in practice, not just on paper.
Evidence collected during control testing varies widely depending on the control and the testing method. Evidence may include screenshots, system logs, configuration exports, access records, tickets, or workflow outputs. Manual testing often produces narrative evidence that explains how a control operates, while automated testing produces structured outputs that show system state. The quality of evidence matters more than its format, because evidence must support a clear conclusion about control existence and effectiveness.
Poor evidence undermines assurance even when controls are strong.
Good testing produces evidence that is clear, reproducible, and defensible.
Sampling strategies determine how many instances of a control must be checked to achieve confidence, especially when full coverage is impractical. Manual testing almost always relies on sampling because reviewing every instance would be prohibitively expensive. Sampling must be deliberate, selecting instances that are representative or high risk rather than convenient. Automated testing can reduce reliance on sampling by expanding coverage, but even automation may sample when testing complex workflows or external dependencies. Sampling decisions affect the strength of conclusions, so they must be aligned with risk tolerance and assessment objectives. Poor sampling leads to either false confidence or unnecessary alarm. Control frequency influences how often testing should occur to remain meaningful.
Controls that change frequently or protect high-risk assets require more frequent testing than static or low-impact controls. Automation enables higher frequency testing without proportional increases in effort, making it well-suited for dynamic environments. Manual testing is typically less frequent due to resource constraints, which makes it better suited for controls that change slowly or require human interpretation. Aligning testing frequency with control behavior and risk ensures that assurance remains current. Infrequent testing of fast-changing controls creates blind spots that attackers can exploit. False assurance is a significant risk when tools report status without validating actual function. A control may be enabled in configuration, but disabled in practice due to errors, exceptions, or integration failures. Automated tools may report compliance based on configuration flags without confirming that the control actually enforces policy. Manual testing can catch these gaps by observing real behavior and outcomes. This is why relying solely on tool output can create a misleading sense of security.
Effective testing validates outcomes, not just settings.
Exceptions and compensating controls require special handling because they fall outside standard control patterns. When a primary control cannot be applied, an alternate control may be used to achieve similar risk reduction. Testing these scenarios requires understanding the intent of the compensating control and validating that it truly mitigates the risk. Automation may struggle with these cases because they are often context-specific. Manual testing is usually necessary to assess whether exceptions are justified and whether compensating controls are effective. Poor handling of exceptions is a common source of control failure. Findings from control testing must be evaluated with severity and impact context tied to the control's objective. A control failure does not automatically equate to high risk if the protected asset is low impact or if other controls reduce exposure. Conversely, a minor seeming lapse can be critical if it affects a high-risk process. Contextualizing findings prevents overreaction and underreaction alike. Clear linkage between findings and control objectives helps decision-makers understand why an issue matters. Testing without context produces noise rather than insight. Manual and automated testing are not competing approaches, but complementary ones that together provide meaningful assurance. Manual methods bring judgment, context, and the ability to interpret human behavior, while automation delivers scale, consistency, and frequency. Control design and operating effectiveness both benefit from using the right mix of methods. Evidence quality, sampling discipline, and appropriate testing frequency determine whether results can be trusted. When organizations balance manual insight with automated validation, control testing becomes a reliable measure of security rather than a ritual.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.